Hey, students, let me go ahead and address this question. I got an email, wasn't a real long question, and then I read it and I said, ooh, this is going to be really a challenging problem, mostly because of step number one. And remember, step number one is get a good physical picture of what's going on. So let's talk about elevators for a little bit because this is the part the working part, the engineering part, the stuff behind the scenes that you may not be familiar with. In fact, I'm quite sure, and it's very complicated, and they're not all the same either. So this problem can be interpreted a bunch of ways, and that was my concern about this. So let's talk about this. It says. Find the useful power output of an elevator motor that lifts a 2,500 kilogram load to raise, to a height of 35 meters in 12 seconds. And it also accelerates the speed from 0 to 4. All right, so if I made this big building here, and of course, at least here in Santa Barbara. Now, we never see these real tall buildings. But if I had an elevator shaft here, somewhere in the building, put the motor up here on the ceiling or the roof. And so there's maybe this elevator down on the lobby floor here. And then this long cable that goes all the way up to the motor. There's going to be some kind of tension pulling it up. Okay. Now, to help it go up, there's often some counterweights. And here's where this can get a bit messy, if you will. Let me not draw it real well, but let's say the counterweight is over here somewhere. And so some of these systems can get quite sophisticated where they can add and take off counterweights as things go up and down. And so we can store them as they go up and down. And so that's what this one is trying to say when it says here, note that the total mass of the counterbalance system is 10,000 kilograms. Okay, so what they're trying to say is that the two of these together are 10,000. So I'm going to put that over here, 10,000. The whole system, not just this counterweight, but also this whole elevator together. But when it says right here, back at the beginning part of the motor, to lift the 2,500. They don't mean that this is 2,500. What they mean is this is 2,500 more than that one. And the two together add up to 10. So in other words, as this weight comes down and the elevator goes up, there is a net effect of lifting 2,500 kilograms. Maybe I shouldn't have put that right here. Okay. Maybe we could do something like this. If you call that A and that B, you might say A plus B is 10,000. But the heavier one, B minus A, is 2,500. So if we did a little math here, like add these two together, we would get 2B equals 1250. Cut it in half, and we're at 6,000 6,250. So we're really saying this one down here is 6,250. And let's see, what do I get when I take 6,250 and subtract then, so that'd be B, subtract the 2,500 to get A, this would be 3,750. Now, we don't have to do all this work. This is just me kind of talking about what they mean when they use this phrase. Where is it? Note, the total mass of the counterbalance system. So these two added together. And you can see 3,750 and 6,250 each make a total, or adding up to 10,000. And that this, when you subtract from that, is 2,500 more. That's why they kind of give this. They say so that you're only equivalently lifting the difference, 2,500. But both of these are going to be moving. And so it says the full 10,000 gets accelerated. That's the key to this problem. Now, we could go into a little bit more of how the elevator works, but I already did way too much. This right here, this little note, is going to be a key statement, because I want to know how much power, which is energy divided by time. So I'll start with energy. How much energy this motor needs to put out. So what I'm going to say here, and this would be my kind of my step 2 here, once I got a good physical picture, is now, and since I'm not doing forces, I won't necessarily do a free body diagram, but what I will say is some of this energy goes into what we call gravitational potential energy. And so some of it goes to MGH. And some of it goes to kinetic. And when you add the two together, you get the total. And that's why this phrase here is important, saying that it's the equivalent of just lifting 2,500, because again, one goes up and the other goes down. So I'm going to put 2,500 kilograms. I'm going to multiply by 9.8, and I'm going to say we are going to lift it 35 meters. All right. So that part, 2,500 times 9.8 times a height of 35 tells me that 857,500 joules of energy are added to this counterweight system. And so notice that's a lot, less than if I just was lifting this by itself. So that's the advantage of the counterweights. We don't have to have so much energy going to the motor and so much weight, and such a big motor. We'll have a counterweight system. Okay. Now, the other thing, though, is these masses are going to be moving. And that's what they're trying to say here, is that this right here was the net effect of both masses, one going up and one going down. But when it comes to kinetic energy, they're all positive numbers. Whether it goes up or down doesn't really matter. It's velocity squared. You could, if you wanted, say how much energy did it go to lift up the elevator and use the full weight of the elevator, and then subtract off how much potential energy was given back by going down, and that difference would be here. And then you would maybe look better, because then you're saying, okay, I'm doing the two separate. And then likewise, I would do here. I could say, what's the kinetic energy of B? And then I would add that to the kinetic energy of A. They're both moving. I wouldn't be subtracting them, because it's not like it's an up or down, plus or minus. It's a V squared. They're all positive. So that's why they're trying to help you here. And it says, but the full 10,000 is being accelerated. So this would be 1/2 times 10,000 times its speed is 4. In fact, maybe that's worth going back here. If we take, 35 meters and maybe give us 4 meters per floor, we're probably looking at the 8th or 9th floor. And so, again, something that you guys may not be as familiar with being here in, we don't have these big, tall buildings, but these would be what they call express elevators in big cities. And so you go faster, 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 and by the time you get to the 9th floor, you're not even close to where you want to go. You're trying to get to the 100th floor. And you just got to get to a high speed. And then the motor maintains that same high speed, so you don't keep accelerating. So the motor doesn't have to put out as much power, but it still has to supply power going on up. And you still have, if you're on the 9th floor and you're trying to get to the 100th floor, you still have 91 more floors to go. So you're only 12 seconds in, and you've still got quite a ways, time in there. So you can be, in that elevator for a whole minute. But these express elevators, never stop between the lobby and the 100th floor there. So that's how you can get so many people. Could you imagine being on an elevator, stopping on every floor like we're probably used to in our 5 or 6 story buildings here in Santa Barbara? And, we're like, oh, it takes forever to get to the 6th floor. Could you imagine going and stopping, or the potential of stopping on every floor on some of these tall buildings? So anyways, that's something else that needs to probably go into your understanding of this step 1. How does an elevator work in order for this to make any sense here? Okay, well, in either case, let me put this off to the side and come back here and say, well, how much energy is this? So 1/2 times 10, 3,000 times 4 squared. This is an energy of 80,000. And so the motor had to give the total of these two. Had to give enough energy to lift the counterweight system as well as give it some speed. And so let's see if I add these together. 13, carry 1. All right. So 937,500 joules is the total energy that needs to come out of this motor. Now, power, or just P for short, is the amount of work or energy per time. So we have 12 seconds for this to happen. So this would be 937,500 joules within 12 seconds. And so if I take this 937,500 and divide it by 12 seconds, I'm looking at about 78.1 thousand, so kilowatts. And so a joule per second is a watt. So I need about a 78,000 kilowatt motor for this, or, well, probably a bigger motor because of other scenarios that could happen. But in this particular scenario, we need to be running this motor at a rate of 78,000 watts. Okay. Now, that's probably the easier part, the harder part of the problem, because now the easier part, although again, there's some units here that you may not be familiar with. So again, more reason I wanted to do this. In fact, well, let's say watts and kilowatts and joules. Okay, so you're familiar with those units. But a very interesting unit for energy is one that we don't usually use in a science class. It's more of an engineering one. If you pay your electric bill, you'll see at the end of the month, it says how much energy did you use, and they'll list so many kilowatt hours. And so coming back to this little formula here, work slash energy would be power multiplied by time. And in a science class, we usually put our power in watts, which means joule per second. So then we put our time in seconds, and then we come out with our energy in joules. And that's how we've been presenting it. And that's very useful, although there are other units, as you can imagine, just like there's all kinds of units for distance, like a foot or an inch or a meter or a centimeter, or some old ones we're not as familiar with, like I guess a yard you are, but how about a chain? There's one you don't hear much. A chain. What is a chain? Must be a tenth of a mile. In fact, that makes me think about an acre too. We use acre for area, but we also use square meters or square feet or square inches for area. In fact, what is an acre? An acre is a rectangle that is one chain by one furlong. Yeah. And nobody uses a chain or a furlong, although we use acres still quite a bit. So I guess this is a tenth of a mile, which makes it 22 yards, which makes it 66 feet. And a furlong, let's see, what is it? A mile cut in half is a half mile, cut that in half is a quarter mile, cut that in half is a furlong. So this is an eighth of a mile. Oh, wait. I said that wrong. Okay, good. Yeah, something was really bothering me. It's a tenth of a furlong. That's what a chain is. Yeah, because a furlong is an eighth of a mile, and an eighth of a mile is 200, and like a 220 back in the old days. Now it's 200 meters, but the old race around the track. Anyways, I digress too much, but I am kind of curious. If I multiply by this is 3, this is 660 feet, and that's why if you take 66 feet and multiply it by 660 feet, you get the very famous 43,560 square feet in an acre. Well, I apologize for the significant deviation from the problem, but let me go back to the problem. And the reason I want to go back to that problem is because I was trying to say here that if you take any units then of power and multiply it by any units of time, it would technically be a unit of energy. And when I started digressing into unused units or seldomly used units, what I was trying to say here is one power unit is a kilowatt, and one unit of time is an hour. And so a kilowatt times an hour is a unit of time. Now, it wouldn't be a joule, because a joule is what you get when you take a watt times a second. Now, obviously, we could convert kilowatts into watts, and we can convert hours into seconds and figure out what this is. And this doesn't even have a fancy name. It's just called a kilowatt hour. So a kilowatt hour is a way and a unit to measure power. And again, you may not be familiar with it because it's not usually used in the metric system or in a science class. It's used more in the business world as well as in the engineering world. Okay, so keeping that in mind, let's do this. If I come back to the problem, part B, and part B says, what does it cost if electricity costs, it looks like 9 cents, wow, I wish it was that cheap, per kilowatt hour. Okay. So if you're looking for, your total dollars, it looks like my pen's getting a little dry there. I'm going to have to get a new one. Let me just switch over to red for right now. Okay. So if you are looking at how much does it cost you, you would look at your rate multiplied by your time. Kind of like if you wanted to know how much money you were going to make, you would take your rate. Let's say you're making $20 an hour, and you say, okay, I have a little bit of time I can work. They're going to call me in. Maybe I can commit to 3 hours, but I really got to study my physics. But, if I know I make $20 an hour and I go into work for 3 hours, I multiply them together and I make $60. Okay, so I'll make a quick $60 and then I'll get back to my studies. Same thing here. My rate then is what, they are saying, but it's not a rate of time. it's a rate per kilowatt hour. It's saying $0.09 or 9 cents per kilowatt hours. So I need to multiply it by the number of kilowatt hours. So there is our energy. And energy is power multiplied by time. And so this is how I got into this discussion about one way of getting energy is to list it as power in kilowatts multiplied by time in hours. So for this motor, we've just concluded in part A that it is 78.1 kilowatts. And our time in hours needs to do a little bit of conversion because I have 12 seconds. And so I want to get rid of seconds and convert it to hours. And so jumping back to chapter 1, I would say I'm just multiplying by a unique number 1, which would be 3,600 seconds in 1 hour. So then that would convert my time into hours. So 12 divided by 3,600. And so we are talking about 0.003 repeating for the number of hours. And so seconds would cancel off. So now when I multiply these two together, I am going to get the energy from this motor in kilowatt hours. So let me multiply it then by the 78.1. And we are looking here at about 260 kilowatt hours for the amount of energy. And in kilowatt hours, I can now feed it into there. So I will put that into here for kilowatt hours and then multiply by my 9 cents. And we're looking at about 2 cents worth of electricity for this to work. Yay. And maybe that was a little harder than I gave it credit for. Or maybe I was just long-winded because I got talking about different units, and particular units we don't use much. But like I said, hopefully that led you to some units that is used a lot. It just may not be used by you, and certainly wasn't presented to you in a science class here. So I guess that's why it's in that harder book, which is designed for as an engineering book, and that's probably why it's in there. So maybe a little bit of an unfair question to you, but hopefully this video helps with your logic, and now you understand it. Take care.